Okay, we'll start our today's session. A very good afternoon to one and all. Last class we were discussing about block ciphers, right? And now we move on further with the modern day block ciphers. So we just saw there are two type of ciphers, that is stream cipher and block ciphers, and most of the symmetric key ciphers fall under block ciphers, right? And which encryption technique they prefer, whether they go with substitution technique or transposition technique. I hope you people remember from our module 1 where we started a discussion based on substitution techniques starting from Caesar cipher, then we came across Playfair and Hill cipher kind of stuff. Then we moved on to transposition technique. So assuming that you people are clear with what even by substitution transposition, okay, and modern day block cipher is going to have a combination of both, but comparatively they prefer substitution technique over transposition technique. And all our modern day block ciphers will be made up of zeros and ones alone, right? To be more resistant to brute force attack like exhaustive search attack kind of thing, modern block cipher mostly they go with substitution cipher. So you'll see an example here. There is a situation that you have a block cipher where each block is made up of 64 bits. Okay. And the attacker or the third party person has a knowledge that there are 10 number of ones in the ciphertext, that out of 64, okay, 54 will be zeros and 10 will be ones. So that is the only clue here. I mean, he can able to grasp, and he will be trying to make a trial and error method to attack your ciphertext, right, to get your plain text back. So assume that suppose the same information is obtained. The first scenario, the cipher is a substitution cipher, and second one is a transposition cipher. So substitution cipher means each and every character in the plain text is going to be replaced with some other character. That is, if 0 is there, there are high probability that 0 would have been replaced with 1. If it is 1 is there, there are also a possibility that 0 will be replaced with, sorry, 1 will be replaced with 0. But assuming that there are 10 ones in the ciphertext, it's not guarantee that the same number will be there in the plain text if you're going with substitution cipher. So under such scenarios, he has to try nearly 2 power 64 times, okay, of this trial and error method to break the text if the encryption technique is a substitution cipher. Whereas if he has have only this one transposition cipher, and he has a knowledge that only 10 number of ones are there in the ciphertext. In transposition cipher, only the position of the ones are going to change, right? So totally we'll have only 64 factorial kind of combinations he has to try. So it makes somewhat easier for the attacker to able to retrieve the data from the ciphertext if you're going with transposition cipher when compared to substitution cipher, right? Because the 10 number of ones means just a combination of 10 ones among the 64 is very easy compared to 2 power 64 times, right? So I hope you people now get an idea why they prefer substitution cipher over transposition cipher. If it is clear, raise your hand. If you have any doubts or any queries over this point, you can ask me now. Right. Now we move on to a next topic called permutation group. Okay. Okay. Don't think that what is a jump from this substitution transposition concept towards permutation group. Okay. This permutation is nothing but a transposition cipher technique. What certain people think, in the sense, if I keep on involving multiple iterations of transposition cipher, which is also called as permutation. Okay, there is no use. That is the only thing they want to prove here. For example, if you take this scenario, okay, so this is some green color box which is going to permute your input based on this key. Okay, so here you can able to see I have the input pin number 1, 2, and 3, and the input which is ever coming to 1 is pushed to 2 here, and input coming to 2 is pushed to third position, and 3 is pushed to first position. So here what this number denotes in the sense, 312. So here the first one is 3, which is nothing but the value. Value is 3. The values always denote the input. And the position of the value is, it is placed in the first position, right? Which is the position. The position gives me the output pin. This is always have to be remembered whenever permutation is done. So if the number is 312, we'll be taking the third pin, place in the first one, and if 1 means 1 is a position, I mean value is 1, so you'll be taking the first pin here, it is placed in the second position, so you'll be giving the output in the second pin, then 2 is taken, then 2 is given as output in the third pin, right? Now I'm again connecting another bots with a different key of 1, 3 and 2, right? So 1 just coming directly here, it goes to 1 here, right? And 2 which is coming here is pushed to position number 3 based on this one. And the second pin which is taken as output here is placed in third position, and 3 which is placed here is pushed to the second position here. So you can say I can even add one more box and go on. So what is the point here they want to prove here in the sense, for example, if you take this 2, right? 2 traveled from here, came to 3, from 3 came here, and it again came to 2 here, right? And if you take your point 1 came here, which came to second position, came to second position here and came towards here and moved to 3. You can able to see 2 is mapped to 2 here and 3 is mapped to, 1 is mapped to 3 here, right? And if you go for the third pin here, it traveled from here to first pin and came all the way to first pin and again directly came to first pin. So 3 is placed in first position. So I'll be making a new key called 3. In second position, I found 2. So directly 2. So no issues. Right. And the first pin has traveled from 1 to 3. So 3 to 1. So if I use a single bots which has a combination of 3 to 1, you can able to see this 3 to 1 can able to perform the same operation whatever you did with 2 bots. So the single bots can able to perform the operation of 2 bots altogether. If you're going for a transposition transposition based cipher techniques. What the point they want to prove here in a sense, like in this example, we have 3 input and 3 output, right? So there are 3 means totally 3 factorial different keys can be found that are so 6. So 6 combinations are here. Able to see, and all the 6 are here. This is a table for 2 rounds of iteration. That is, for example, if you take 2, 3, 1 as a first round of the thing, then if you went for 3, 2, 1 for the second round of permutation, it can be done using this 2, 1, 3 bots itself. Right. So here what they want to do in the sense, so a set of permutations is nothing but like 2 or more permutations you're going to perform. It cannot strengthen the security here. The security is not going to be strengthened. You can able to see it cannot strengthen the security of cipher by simply increasing the number of permutations, because you can always find a permutation combination which can able to perform the same operation whatever the amount of iteration you go on. So this is called a permutation group. So permutation group, okay, can be invertible also. You can able to find the inverse of this one. Okay. So whatever you do with this one, with the permutation groups, or that is you combine multiple permutations, you can able to replace it with a single permutation box. Is it clear, guys? This point? If it is clear, raise your hand. If you have any doubts, you can ask me now. Okay. Now we move on to the next one. Okay. Full size key transposition block ciphers. Whether your block cipher can be a permutation group or not. In that we first see full size key. There's a partial size key also. But as of now, for discussion, we'll take full size key transposition block cipher as a first example. As I said, transposition means we're only going to change the position of the characters here. So the only point you people have to remember here in the sense, if you have a full size key transposition cipher, so what are different possible combinations of keys are there? So it can be decided with n factorial combinations. And what should be the size of the key? Size of the key is denoted by log to the base 2 of n factorial. If you see the previous example where we had a 3-bit block which has a 3 input and a 3 output combination, right? So here the bit of the main block size is 3, n is equal to 3. So your total combinations of keys will be 3 factorial, which will be giving me 6 elements, and the size of each key is log to the base 2 of n factorial, which give me 3 bits long. That's why we had this one 3-bit input, 3-bit output. We had 6 elements of combinations, and each element is made up of 3 bits here, right? So now if you move on to a full key size substitution block ciphers. So transposition we had n factorial. How does this substitution cipher works on? As we are dealing with modern day block ciphers, we are not going to with characters. We are only going to deal with ones and zeros, right? So here the only point you have to remember is nothing but the total number of permutation combinations which can be found in substitution cipher is 2 power n factorial. Can you able to see? Even the same 3-bit block if you have, okay, 3 cross 3, I'll be having 2 power n combinations, n factorial, that is 8. 2 power 3 is 8, right? So you'll be getting 8 factorial to be 40,320 different keys you can able to have, and the size of the key will be log to the base 2, right? Log to the base 2, 2 power n factorial, which gives me, in this example, log to the base 2 40,320 gives me 16 bits. So here what I will do in the sense, I'll convert this 3-bit into 8-bit input, then I'll do some permutation here. Okay, this is only for your understanding. That is here how to use the key size and the different combinations of key. So here the key size you people have to remember 16 bits, and total we have 40,320 elements. Now you can able to see the same 3 cross 3, okay, in transposition cipher. We had only 6 combination, whereas if you go with your substitution cipher, we had 40,320 different variants of keys. So just imagine how robust your substitution cipher is looking like, right? So to be specific here, the only thing you people have to remember in the sense, if you have a n-bit blocks on a transposition cipher, you'll be having n factorial number of different keys. For substitution cipher, I'll be having 2 power n factorial, and the key size will be log to the base 2 of n factorial, and here log to the base 2 of 2 power n. So under which trade-off your substitution cipher is giving this much security in the sense, substitution cipher will be highly complex compared to transposition, and the size of the keys and the different combinations of keys are more. So obviously it's going to occupy more memory. Under these trade-off, I'm going to provide a better security by giving you with a highly sophisticated and attack resistant algorithm if you use your substitution technique over transposition technique. Right. So I hope it is clear. Right. And the partial key cipher will come across this one while we're discussing the algorithms. So is it clear, guys, so far? Anyone have any doubts in this one? You can ask me now. If it is clear, raise your hands. Okay. Now we move on to the most important topic in our module 3. So what are nothing but the components of modern block cipher. So if you take any present day modern block cipher, everything will be built upon these basic blocks alone. We can't able to find anything apart from this one. Okay, we'll be finding the modern block ciphers using this components alone. To start off with, the modern block cipher is majorly made up of two boxes called P or D boxes. The name P stands for permutation bots. D will come later. Okay. Then we have S bots. S stands for substitution unit or substitution bots, and we have other units also. We will be discussing this. To start off with, I'm starting with P bots. P bots is nothing but called as permutation bot, which is going to perform a traditional transposition cipher. So whenever there's a P box, it's going to perform a transposition cipher. So it's going to change the positions of the bits, okay. And it's generally it is be a keyless bots, okay. And there are three different types of P bots available called straight P bots, compression P bots, and expansion P bots. Right. Start off with the straight P bots. The number of inputs and number of outputs will be always same here. Okay, that way it will be getting n factorial total mappings of this one. As we just saw, okay, the permutation group is called a straight P bots. It is a 3 cross 3 P bots. So these are 6 different combinations of these P bots. And in your algorithm, you'll be choosing any one bot and you'll fixing it in your algorithm. Okay, so it's like a fixed key, right? Here comes the example of a straight P bots when your number of bits here is 64. So this is 64, one of the combinations. Totally we have 64 factorial combinations of bots. This is one of the bots where you'll be taking the 58th pin of the input and will be taken as the output at the first pin, and 50th pin of the input will be placed at the second pin in the output, then 42nd pin, and goes on. Like this is how a straight P bots works. And here they're asking you design 8 cross 8 permutation table for a straight P bots, and the condition is nothing but this P bots should move the two middle bits. That is, you take a bit number 1, 2, and goes on up to 8. The middle bits will be 4 and 5. They're asking you to move this 4 and 5 towards the end, and you can put the rest of the bits in the same position. So how the straight P bots will look like? That is, if you have a bots here, 1, and you have your one outputs here, 8, right? How this combination is going to work in the sense, the first condition is take the middle bits and put at the ends. So 4 will go here, 5 will go here, and you can put rest of the bit in the same position they said, right? So first position 4 came, so 1 will come in the second position, 2, this one comes here, and 6 will be placed in the fifth position, 7 will be placed in here, 8 will be placed in this position. So right, you'll be writing this one 4, 1, 2, 3, 6, 7, 8, 5. Right. Can able to see the relative positions or relative positions in the fence? If you are bringing down 1 to 2, 2 to 3, these things will be 1 second, guys. Sorry. Okay. Only the first 4th input and the 8th output. Check the difference. I mean, take the different values of input and output here. The rest of things are following the same order 2, 3, 4, and other things, right? Now move on to your compression P bots. So most of the modern day block ciphers we use is compression P bots. So the compression P bots are unique features, nothing but here we'll be having different number of inputs, n input and m output. Under one condition, here your output will be always lesser than your input. That is, some compression will be done. Here is an example of a 32 cross, yeah, n, that is 32 input and only 24 output. So what they will do is they will drop certain pins here. So here we will be having different combinations of this 32 cross 24 permutation compression bots. So there, according to the particular bots, they will be dropping certain values. For example, here we have 1, 2, 3, 4, 5, 6 is there, 7 is not there, 8 is not there, 9 is not there, and goes on. Like this, they are dropped certain bits so that you'll be getting only 24 bits as the output here. Next comes the expansion P bots. Here also we'll be having two different numbers of inputs and outputs. So n input and m output, right? But here the input will be lesser value and your output will be in a greater value. So how they are going to expand here, since they are going to repeat certain input bits here. For example, the first bit is repeated here, right? Third bit is repeated here. Ninth bit is repeated here. Like this, they will be repeating certain bits not to make this 12-bit input into 16-bit output here. Right. So these are different combinations of this P boxes. So anyone have any doubt in this P bots permutation bots? You can ask me now. If it is clear, raise your hands if you have doubts, so that I'll move on to the next property of this P box as well. Okay, right. Now we move on to the next one called invertible property. So if you're using any of these P boxes in your encryption, I need something in the decryption part, right? So certain boxes alone will have this invertible property. So if you consider P bots, only your straight P bots will be invertible one, but not your compression as well as expansion P bots. How we can able to get the inverter version of a straight P bots? If we properly remember in transposition cipher, where we made this column shift other stuff in our module 1, we just made this one how to find the decryption key. The same concept is used here. This is your encryption combination of your straight P bots. You just name the add the indices, swap the indices, and if you sort them, you'll be ending up with the new key which is be used as the decryption part. So these two boxes are invertible to each other. Okay. Whereas if we go for compression and expansion pivots, we can't find the inverses because in compression you'll be dropping certain inputs. So while doing the reverse process, we can't able to generate the bits which are dropped. And for expansion pivots, if you are repeating the bits, like for example here one is repeated here 2 times, we can't able to combine these two and we can able to regenerate the bit which is repeated here. So compression and expansion P boxes are non-invertible ones. Now we move on to the second important bots called S bots, which is also called a substitution bots, which is going to perform a miniature substitution cycle. It's going to substitute each and every character in the input with some other character. So here S bots will be always represented as M cross N substitution unit, and it is not mandatory that M and N are mostly same. Sometimes it will be same, sometimes it will be different. So here it doesn't matter. We can easily, without dropping, we can able to compress as well as expand the values in S bots, okay, without dropping or without repeating also. That's why here the values of M and N are not mandatorily same and all the time. So here how in the sense the relationship between the input and output will be based on some math, basic linear equation will be playing a role here. For example, you have n number of inputs which is going to produce m number of output. For example, here you can able to see the first output y1 is depends upon some function, mathematical function is going to relate all these inputs here. And y2 is using second mathematical function, it's going to relate all the inputs here. Like this, I can able to generate all the outputs with respect to the inputs and the respective mathematical function. I will directly jump into an example so that you get a clear picture. So here you can able to see output input, so input output relationship of X bots, which has 3 cross 2. That is 3-bit input and going to produce 2-bit output. So how this is actually this white one is your S bots here. Okay. So what they will do in the sense, they will take the leftmost bit of the input and they define it as a row, and the rightmost bit will be taken and will be defined as a column. For example, here if you want to transmit a value called 0, 1, 0 via S bots, so 0 means this row, next 1, 0 is this column, and this is the value. So 0, 1, 0 will be replaced with 0, 1. Similarly, if you take 101, 1 means this column and 0, 1 is, sorry, this row and this column, I'll be getting 0, 0. So 101 will be replaced with 0, 0. So 3 bits have been converted to 0 when 2 bits in the substitution manner. So there is no dropping, nothing stuff is used here. Simple change in the values alone has been done here. But using this lookup table, right? Invertible property, when you come to S boxes, okay, not all S boxes are invertible. So there are certain S boxes which can be invertible based on the mathematical expression we choose. Like how we have in P boxes, if both input and output are the same values, you can able to get the invertible property. Here sometimes when M is equal to N, box may not be invertible. Sometimes when M is not equal to N, sometimes the box will be invertible also. So it is not mandatory that all so and so bots will be invertible kind of thing, right? You can able to see this is an example where a 3x3 S bots. Okay, this is a bots used for encryption bots, and this is the bots used for decryption here. Okay. You can able to see here I have an input of assume that 001, right? So 00 is here, right? And okay, fine. Okay. So you'll be taking the leftmost bit 0 and 01 is here the column, the value is 101. So 001 is now converted into 101. Suppose this 101 is given as input to the decryption end. Here 101 goes, so I'll be using this first row. 01 is this one column. I'm getting the value 001 back. Okay, so this is used for encryption, decryption, and they are invertible to each other, right? So anyone have any doubt in this S bots? You can ask me now. If it is clear, raise your hand. If you have any doubts, you can ask me. Because it's a very, very basic thing you people have to understand. That's why. Okay, only one and one. Okay. Now, the most important thing called exclusive OR. Why I'm saying this important again in the sense this exclusive OR plays major role in symmetric key ciphers. So in symmetric key cipher, we'll be using the same key for both encryption and decryption, and this exclusive OR plays major role, especially in cryptography, as we already saw in our polynomial arithmetic. Whenever you are going to perform an addition or multiplication, okay, everything moves into XOR operation, right? The same thing here. For example, if you assume you're transmitting a bit called 0 and your key is 1, can anyone tell what is the value of y here? I'm going to XOR this X with key 1. What will be the value of y? 0 XOR with 1.
0.
0 XOR with 1. What will be the answer? 1 actually, right? 0 XOR 1 gives me 1. And suppose in decryption part, if you give the 1 here, again the same key is used, you'll be getting your 0 back. This is the unique specialty of XOR, that is you can able to use the same key value under XOR operation. That is where you're going to mix your key with your input. I can use the same XOR operation both encryption and decryption end. Okay. So because as I said already, addition, subtraction, other binary operations in Galois field of 2 power n, we'll be using exclusive OR operation here. So I hope everyone remember Galois field or simply field. Field will be satisfy all the 5 properties. Okay. So invertible, as I said, both are invertible to each other. The next component is circular shift. Okay, that is we can able to shift the incoming bits a certain number of predefined value. For example, here I have 8-bit word. Okay, and I can able to make a 3-bit left shift at the encryption end. So the first 3 bits B7, B6, B5 have been taken and shifted left, and they place at the end as B7, B6, B5. And they are invertible component because if I am shifting left 3 bits at the decryption end, I will be shifting towards the right hand side the same number of 3 bits to get my uh, data back, right? Next one comes the swapping operation. So this is a special case of circular shift operation. The what we just saw here, the same condition here, but only thing is something but here where your total number of bits should be always even number. Sorry guys, once again. So it should be always even number. So here n is 8-bit word means I'll divide them into equal halves and I will swap them. That is, if you have a left and right hand side, this left will come this side and this right will go this side. Right. And the decryption will do the reverse process. And next one comes split and combine. Okay, this is also other operation, again operating on a even number of bits here. That is, I will be splitting them into equal half. Then I will do some manipulations or any mathematical operations which is required to do. Here I will do some manipulation, assume that I am doing some XOR and other stuff goes on. Here also I will be manipulating them with other mathematical operation goes on. At the receiver end, once I receive this one, okay, here at the decryption end, again I will be, after decrypting, I will be combining them. This is called split and combine method, right? So with this, we conclude the various components. So if you see the components which we just saw is a P bots. P bots also has other name called D. We will see what is the D stands for. Then we just saw S bots, right? Then we moved on XOR. Then we have circular shift. At last we had swapping. Then split and combine. So only these 6 operations will be carried out in our modern day block ciphers, especially in our uh, modern day symmetric ciphers. So anyone have, I mean, I hope you are clear with all this basic building components here. If you are clear, raise your hand so that we move on to the next topic. One more topic, we'll conclude this session. If you have any doubts, you can ask me if it is clear. Okay, it's a very basic here. Yeah, thank you, Arun. Yeah. Now we move on to product ciphers. So one of the most pioneering technique or algorithm which came into existence for modern day block ciphers founded by Claude Shannon. I hope you people have heard of Shannon theorems, Shannon capacity theorems, formulas, other things you would have heard of. Same person also discovered this process also. What he did then, since he created a block cipher called product cipher, which is going to use the combinations of substitution, permutation, and the other components also. Yeah. The specialty of this product cipher is in the sense it is going to satisfy two important property called diffusion and confusion. So what does this diffusion property and confusion property says? In the sense, okay, if your algorithm is going to satisfy a diffusion property, then it means that it's going to hide the relationship between your cipher text and plain text. That is, if you have your encryption algorithm here, we are going to give you the plain text, which will be encrypted using a key called K, and I'm going to get my cipher text here. So how each and every character in the plain text is mapped to cipher text. If this relationship is hidden, then you are satisfying the diffusion property. And this part is taken care of by all your P boxes. You take care of this diffusion property. That's why this P bots is also called as D bots. Right. Next comes the confusion property. So this confusion property is going to hide the relationship between my cipher text and the key. That is, there will be always a relationship because this key is going to be taking part in some mathematical operation inside this algorithm. So this relationship between key and cipher text, if you're able to hide, then your algorithm or your product cipher is going to satisfy this confusion property, and this is taken care by your S boxes. Right. Is it clear, guys, regarding diffusion confusion property? If it is clear, raise your hand. Okay. Now I'm introducing a new term called round. Like how we have iterations in block ciphers or modern day block ciphers, we use a term called round. So we'll be having more number of rounds for a particular algorithm. So if I say a round means round can induce both diffusion and confusion to your plain text. Okay, and it will use combinations of S boxes, P boxes, and other components. And this is how a product cipher made up of two rounds will look like. Here you have a block made up of 8-bit. Okay. So this 8-bit is first given to a key mixer. Assume this key mixer is going to perform XOR operation. So yeah, all these 8 bits is going to be XORed with the incoming key. This key is called as your round key. And this is a thing I'm introducing to you first. This is called round key. And this key is called as your encryption key. Okay. So whenever you just see any block ciphers like how we just saw here, slides back. If I say key here means this is the encryption key, but this key not directly involves the operation here. Okay, what it will do in sense this key will be given as a input to a round key generator, and this round key generator will create individual keys specific to particular rounds. So K1 is a round key for round 1. So here the XOR operation will be happening and it will be giving me the same 8-bit as output. So for this 8-bit as output to introduce my uh, confusion property, sorry, confusion property, I'm using 2 cross 2 S boxes, 2 input and 2 output. So I need 4 S bots, which is going to take the 2 cross 2 inputs of this 8-bit, and I'm going to produce again 8-bit as output from these 4 boxes. And to introduce this diffusion property, I'm using a 8 cross 8 P bots. Okay, this is one of the combination of the 8 cross 8 P bots, right? So this is going to produce me again 8-bit. So this 8 bits will be acting as a middle text, and same thing is repeated for the second round, but using a different round key K2. If you want to introduce a third round, then generate a third round key and you can able to repeat these things. So here you can able to see we are having 3 components here: XOR component, S bots, and P bots. This is the basic structure of a product cipher here. So how this confusion diffusion property is maintained? You can just see here, I have the 8th bit here in the plain text. How this 8th bit is going to have an impact in multiple bits in the output, you can able to see here. So the 8th bit is coming as input here, and this K1 will also be made up of 8 bits. In this, the 8th bit will be taken and will be XORed with this 8th bit, and it will be given to as an input to my SPOTS 4, and this SPOTS 4 will be receiving another value from the 7th pin also, right? Okay, as of now, we are just concentrating on how the single bit is going to be manipulated. Right, and now this SPOTS is going to be producing two outputs called 7 and 8, which has impact of this 8 bit 8th bit value on both 7 and 8. Okay, so this 1 to 2 mapping is done. Now this SPOTS 4 has confused you. I mean, introduce a confusion property. We can't able to map how this key K1 is going to be related with your cipher text and otherwise output of this SPOTS. Now the 7 and 8 is now transposed, that is transposition cipher using this P bots move to pin number 2 and 4. Okay, now this 2 and 4 is the middle text is again encrypted using the bit values of 2 and 4 in my second round key. Right. So second round key is going to be XOR here and going to given as a input for S1. This S1 bots will be receiving another inputs also, right? And it is going to produce the output of 1, 2, 3, and 4. And again, this is permitted using my P bots, which is placing the cipher text in 1, 3, 6, and 7. You can able to see how the single 8th bit is having impact on this 1, 3, 6, 7. If anyone changes this 1 bit here, they can't able to retrieve this 8th bit in the output properly, or if anyone touches the plain text here in the 8th bit, it will totally change this entire 4 bits here. So this is how the relationship is going to be meant very complex so that the relationship can't be revealed easily. Here guys, how basic
Sir,
products. Yes,
so
sir.
the rounds key encryption keys is just generating random encryption keys, right? Once we give
Yes,
one input.
yes.
If
Actually,
we only give all the inputs, then there's no need for that, no?
no, you're
So
saying
I just didn't understand what is the need for having that extra rounds encryption key generator.
okay. You are asking what is the need for this K1, K2 if we are supplying this key called K, you're saying, right?
Yes, sir.
Okay, actually this K1, K2 is not random generator. Round key generator will take an input of key called K, and here we will have some mathematical algorithm which will produce this K1, K2, K3. And these values of K1, K2, K3 will be produced exactly at the decryption end if and only if you supply this key called K at the round key generator at the decryption end. Right, no need to share all these round keys at the
Okay.
decryption end. So there he'll use the same round key generator algorithm, but he needs this key at the decryption end also. Because being a symmetric cipher, I'll be using the same value for decryption key also. There it will again generate this key so that it will be used in the decryption end. This is
So
a
it will
basic
have
process.
the same K1, K2 values all the time.
Yes. What you said is
Okay.
correct. This is a basic structure. We'll see like DES, AES, you'll get a clear picture of why we are going with this kind of stuff. Here we just saw only 2 rounds, like for a DES and all, we'll go for 16 rounds, 14 rounds kind of thing. We'll see. I mean, this part is clear, right? It's not simply random things. It is generated using this key K.
Yes, sir.
Anyone have any doubts, guys, apart from this? If it is clear, raise your hand. Then we'll wrap up today's session with this one. Next class, we move on to types of product ciphers based upon the components, whether invertible or non-invertible. Based on that, we can able to classify into two. We'll see those things from the next class onwards.